If you're enjoying Why This Universe, there's another University of Chicago podcast network show that you should check out, and it's called Big Brains. Big Brains brings you the engaging stories behind the pioneering research reshaping our world. Change how you see the world and keep up with the latest academic thinking with Big Brains, part of the University of Chicago podcast network. Today on Why This Universe, we're going to be addressing the question of whether our universe had a beginning, a single moment that started it all. And, spoiler alert, there's a good chance you already know the answer to this. The theory that points to the universe's beginning is called the Big Bang Theory, and by now it's so ubiquitous in culture that there's even a TV show named after it. But as much as we take the Big Bang Theory for granted today, there wasn't always this consensus around it. It used to be that people had no idea whether the universe had a beginning or whether it just lasted forever. And so today we're going to be talking about the Big Bang and also the opposing theory, the biggest challenger to the Big Bang, which is the steady state theory. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
So before we dive into this whole historical debate, let's talk about where the Big Bang Theory came from. We've done an episode in the past about how we know that the universe is expanding today. It's episode 9 if you want to go refer back to it. Basically, Einstein's equations about space and time in the early 20th century taught us that the shape of space could actually change. In fact, the changing of the shape of space around massive objects is what we experience as gravity. But with this discovery came a huge new possibility. It made it possible that the entirety of the space making up our universe could be expanding or contracting. In 1929, Edwin Hubble and Milton Humason made empirical observations that showed without a doubt that our universe is indeed expanding. The volume of any piece of space is growing as time advances, causing distances that separate galaxies to increase. The most mind-boggling thing about this to me is that the universe is not actually expanding into anything else at all, so listen to episode 9 to hear more about that. So let's take this empirical fact that our universe is expanding. What happens if we run the equations backwards? Well, for the universe to look like what it does now, it must have, in the distant past, been in a much more dense and hot state, so that it could expand out and cool to what we see today. And if you rewind this process all the way, you'll get to what seems to be a point where you can't rewind any further, a state when the universe was infinitely dense, right at the beginning of time. This is the basic idea behind the Big Bang Theory. Okay, so before we move on, there's a small disclaimer I have to make before people get mad at me, which is that just because the Big Bang happened, it doesn't necessarily mean that that is the beginning of time. There are some people who like to explore the idea that maybe there was a universe before the Big Bang that collapsed to a point and then re-expanded, and so on and so on, and so maybe this Big Bang moment wasn't really the beginning. But as far as we can tell, and as far as we can test physically, the Big Bang seems to be the moment when time as a concept started to make sense. So for that purpose, in this episode, we'll be referring to the Big Bang as the beginning of time.
So up until the 1960s or so, the Big Bang Theory wasn't the only cosmological model that was taken seriously by scientists. And in fact, it probably wasn't even like the leading or most popular idea about our universe and its history that was on the market. Probably the most popular idea, if I'm reading the history right, is something called the steady state theory or steady state model. The idea behind this idea, or the idea behind this theory, I should say, is that, sure, space is expanding. They believed those observations. But as space got bigger, more matter was spontaneously created in such a way that kept the overall average density unchanged, fixed. So old stars would die off and fade while new matter would come in and create new stars, keeping the same number of stars and galaxies per volume as there was in the past and in the future. So everything's changing while still maintaining the universe in a steady state configuration in this theory.
Right. So in other words, the universe would last forever in roughly the same way that it is now in terms of like galaxies and planets and things like that.
Yeah, it's kind of like an ecosystem in equilibrium. Like people die and people are born, but in equilibrium, you kind of have the same number of people living in roughly the same way, generation after generation after generation. The universe is kind of like that in the steady state theory.
Do you know if the steady state theory came out before the Big Bang or like roughly at the same time, like independently, or if it was a response to people being uncomfortable with the Big Bang and wanting like different options?
So the Big Bang was definitely the first idea. I mean, when you take Einstein's theory of relativity, general relativity, and really you don't do anything else, you don't add anything like the spontaneous creation of matter, you find yourself automatically going to the Big Bang theory. That's kind of just what falls out of it. So people like George Lemaitre and other sorts of people early on were advocating for something like the Big Bang. And people like Fred Hoyle, who was probably the biggest proponent of the steady state theory, came up with alternatives because they didn't like things about the Big Bang theory. So let's explore that a little bit. So Fred Hoyle is this really like famous English astronomer. He's famous for his work on the fusion of nuclei in stars. And by the 1950s, he was like one of the most famous astronomers in the world. Not only for his important research, but also he's on radio all the time. He's writing popular books about physics or astronomy, and he's even writing science fiction. So he's like very out there and has a big public persona. And in fact, as an aside, he's the one who came up with the phrase "the Big Bang." He coined that in a BBC radio broadcast in 1949. It's probably the case that he meant for it to be kind of a derogatory term, like the Big Bang, like something you wouldn't take seriously. But he always denied that. But he definitely didn't think much of the Big Bang theory. And, maybe that went into his decision to call it by that kind of silly sounding name.
Right. And I guess it just goes to show if you are a public figure in science or you're communicating science, the influence that you can have in like the way that you talk about science theories and bring it to public. Like the fact that the Big Bang is still the phrase that we use as physicists.
And I've talked to some of my colleagues who were involved in the naming of certain things, like the people who coined words like wimps and machos and dark energy and things like this. And I think they were pretty deliberate about the branding and how this would kind of shape the story. And you don't end up being the guy who names something without being pretty good at that sort of branding and that sort of communication. And Hoyle definitely had a knack for it.
Right, even science has an element of, advertising.
Sure, what doesn't? So Hoyle never liked the Big Bang theory or really any other theory that talked about the beginning of the universe. He thought that anything that talked about how the universe began was like fundamentally just speculation and pseudoscience. And he just said there's nothing science could ever do to find out how the universe began. So in the view of Hoyle, this was stuff that theologians should be talking about and scientists should just leave alone. So I think that went into his motivation to reject the Big Bang theory and try to embrace an alternative.
Yeah, I'm curious about that because if the Big Bang theory is a science theory, right, it comes out of the physics, it comes out of what we know about the expanding universe, something that like we've empirically shown, like why does he still think it's pseudoscience to bring that, theory to fruition?
Yeah, I mean, I don't know many people who know much about cosmology today who would agree with Hoyle. But there are cosmologists, people who do know a lot about cosmology today, who might say something like this about the theory of inflation, which we've talked about in prior episodes, something an era that took place very, very close to the Big Bang itself. Now, most cosmologists are comfortable thinking of inflation as a scientific theory that could be tested, but some aren't. So maybe just as we get more data and we come up with more ways to test a theory, things that once seemed like pseudoscience can, in principle, become science. But I think it's an important distinction to draw between a theory that's hard to test and a theory that could never, in principle, be tested. To me, those are two very different things. And the Big Bang Theory, to me, clearly falls on the side of, a testable theory, even if in, the early 20th century, it'd be a very hard theory to test, a very difficult theory to test. So there's this story or maybe myth or legend or something about where Hoyle got the idea for the steady state theory. So there was this movie that he went to see. It's a British horror movie called The Dead of Night. And he saw it in 1946 with two other scientists, Thomas Gold and Herman Bondi. So I've never seen this movie, but apparently it involves some sort of mad ventriloquist and his evil dummy. And over the course of the whole movie, there's a plot that advances. And by the end of the movie, the plot has returned to where the movie started. All the things that had changed had reverted to the original state. And you could imagine just the story picking up again and all the same things happening again. So, Hoyle, Gold, and Bondi leave this movie and they apparently start thinking about cosmological models that might look this way. So the universe has events happening in it. Space is expanding. Stars are being formed. Galaxies are being formed. But in the macroscopic sense, the universe is basically left unchanged, just like the world in this horror movie.
Yeah, it kind of sounds like the Infinite Staircases, like the Escher paintings or something like that.
Sure. Or, most sitcom plots where some event happens and something happens to resolve that event so that when you watch next week, you could watch these two episodes in either order and they would make perfectly good sense either way, because nothing really changes in the universe of a sitcom typically. Okay, so in the 1940s, there weren't really any observations that enabled one to distinguish between the Big Bang Theory and the steady state theory. We could tell the universe was expanding. We had some very rough measurements about how fast it was expanding, but we didn't really have any other data to go on. So if you were just a strict empiricist, you could like the Big Bang Theory or the steady state theory or be totally agnostic about the two. You just couldn't tell with the data at the time. So let me ask you this question. So let's say you're an astronomer in 1948 or something. You don't know how this story turns out, but you've been taught about the Big Bang Theory, you've been taught about the steady state theory. Like I said, there's no data you can use to tell these two apart or determine which one's right. What do you think you would think about the situation? Do you think you would prefer one theory over the other, Shalma?
Yeah, I mean, this stuff is always hard to say, and I feel like I always answer this way because I've lived with like the certain knowledge, and so it's hard to imagine coming from zero knowledge how I would feel. But I imagine, I don't know, they're both hard. They're both like hard to understand to an extent. Like it's hard to understand that the universe isn't always in this state or that it won't last forever. But it's also hard to imagine that there could have been a beginning state or something.
When I started researching for this episode, and even when I started writing notes about it, I was going to take the position that the Big Bang Theory was the more sensible thing in, even without any evidence, because if you just take the laws of physics that were known, the Big Bang should play out. That's what Einstein's theory combined with, the existence of matter and radiation, that's what should have happened. But I've kind of convinced myself that that's not so obvious from a 1948 perspective. After all, like the new feature you need to make the steady state theory is a spontaneous emergence of matter, creation of matter. And although we've never seen that, if that was going on, it'd be really hard to measure. It would happen so infrequently that, you wouldn't notice the particles coming into existence very easily. And in 1948, in living memory, there were all these big revolutions in science not that long ago. Relativity and quantum physics, all this stuff, was only a few decades old. So the idea that like the conservation of matter and energy might be violated might have seemed pretty reasonable to a lot of scientists at the time. I mean, all of your, long held, cherished beliefs about Newtonian physics had all been thrown out the window in just the last few decades. Who says anything? There are no sacred cows anymore once you've thrown out all that stuff. So I guess maybe people were just really open-minded about the laws of physics in a way that maybe today we've accepted that quantum physics is going to be the way we think it is, and relativity is going to be the way we think it is, at least to a very high degree of approximation. So I don't know. I'm okay with Hoyle and his position in 1948. Yeah. So what astronomers really needed, though, to break this kind of impasse was hard data that they could use to tell which of these cosmological theories was right, or maybe if neither were right, of what the right one might look like. And the first step towards this happened in 1946 when the Soviet American physicist George Gamow suggested the possibility that most of the nuclei found in our universe today could have been formed in the heat of the early universe in the first few minutes after the Big Bang. This is important because you could, in principle, use the Big Bang theory to calculate how much of these different nuclei should have been created, and then compare that to the abundances you found in the universe. And if they matched, it would support the Big Bang. And if they were different, it would be problematic for the Big Bang and maybe even support the steady state theory. So he started to think about this, and after about 2 years of work, he and his student Ralph Alpher wrote a paper proposing this and explaining how it might have happened. So this paper is one of my favorites for a couple of different reasons. One just has to do with the author list, which is not usually something that makes a paper especially exciting. So I said, George Gamow and Ralph Alpher wrote the paper, but they included on the author list Hans Bethe, who had nothing to do with the paper, apparently. Do you have any guess as to why they might have included Hans Bethe in their paper?
Most common reason someone's name would end up on a paper they didn't write is probably just because they were the advisor to the person who actually wrote it. But I don't think that's the story here, is it?
Well, I, for one, don't put my name on papers that I didn't contribute to. I want to make that clear. But yeah, you're probably right. A few people do. But no, Hans Bethe, I don't think asked to be on the paper. Instead, it was just George Gamow being kind of weird and having a clever marketing ploy. So in the end, the author list read Alpher, Bethe, and Gamow, resembling the first three letters of the Greek alphabet, Alpha, Beta, Gamma. So everyone called this the Alpha, Beta, Gamma paper. It was really punchy and memorable. And today, cosmologists still call this the Alpha, Beta, Gamma paper. And this is the first paper on nucleosynthesis and the Big Bang. The idea laid out in the Alpha, Beta, Gamma paper was that when the universe was very young, it was so hot that nuclear fusion could take place really efficiently. So in this state, the whole universe was really a giant nuclear fusion reactor, kind of like the core of a sun or a core of a star or something, hundreds of billions of degrees or something. But unlike stars, there are lots of free neutrons in the early universe, so this fusion can happen really quickly and release a lot of energy, creating a lot of heavy nuclear elements in a very short period of time. We call this process now Big Bang nucleosynthesis. So this was an incredibly important paper, incredibly influential. We're still talking about it today, most of a century later. But the calculations in the paper are also almost entirely wrong. Gamow and Alpher didn't take into account the repulsion of nuclei, and they otherwise overestimated a lot of the rates for the different nuclear processes. And as a result, they falsely reached the conclusion that the whole periodic table could be generated in the Big Bang. So they were saying all the iron in the universe, all the silver, all the gold, all the carbon, whatever, the bulk of all this stuff was created in the Big Bang.
Yeah, I could see why that would be an attractive conclusion.
It's simple, right?
Yeah.
I mean, yeah, and it would certainly play into the hands of the supporters of the Big Bang theory. I mean, it would seem like that's what you would want if you were a proponent of the Big Bang. And maybe that biased them in their research. Maybe they got the answer they wanted and stopped. I don't know. But it didn't take long for people to see the holes in their arguments and to correct them. within a couple of years, other people had written papers on this that had all the I's dotted and T's crossed. And what they found is that the Big Bang could fuse a lot of protons and neutrons together into deuterium, into helium, and then a little bit of lithium and beryllium, but nothing else. Nothing heavier than that could be produced in the Big Bang in any appreciable or observable numbers. Basically, nothing else in the periodic table could have been created in the Big Bang. Instead, stars had to produce all the rest of that stuff.
So I guess like their big idea was kind of on the mark like that. In the early universe, Big Bang era, you could have this like nuclear fusion and create these larger elements, but they just got their calculations wrong. Do you think today, like those calculations would be like peer reviewed enough to not make it? Or do you think you could still write a paper like that today and publish it?
So literally that paper wouldn't make it through peer review today because there are too many people who know too much about nuclear physics.
Right.
But in 1948, I mean, the nuclear physics was still a new field, and a lot of people, who were very capable scientists didn't know the ins and outs of it in any serious way. And I think if you had a paper on something analogous to that today, something that's a new field where people are still figuring things out, it would not surprise me if peer review would not provide a good backdrop to, or a backstop to that sort of error, that sort of problem. There are lots of wrong papers in published journals today. Mm-hmm. That's you should never trust any one paper just because it says something, because peer review, it catches a lot of the worst errors, but not all of them. Mm-hmm. It also prevents a lot of right papers from being published because the referees don't get it. This is a very imperfect tool.
Yeah, I guess that is an important message nowadays. Like trusting science doesn't mean trusting any scientific paper that you read or finding the one that like supports you. It really means trusting scientific consensus.
Yeah, I completely agree. All right, so let me kind of summarize in a nutshell how the whole process of Big Bang nucleosynthesis works, not as it was described in the alpha, beta, gamma paper, but like as we now understand it with all the correct details put in. So about a second after the Big Bang, the temperature of the universe was like 10 billion or so degrees. There weren't any nuclei at this stage yet, but there were lots of protons and lots of neutrons. Neutrons, if they're not bound up in a nuclei, if they're just free, they'll decay with a lifetime of about 15 minutes. So you have like a window of about 15 minutes to fuse those neutrons into nuclei, or they'll disappear. So that's kind of the window you're playing with. Also during this period of time, the nuclear fusion reactions are only efficient when the density and temperature are really high. And as the universe expands, it's rapidly cooling. So that also puts kind of a time limit on the processes of BBN. You really only have minutes to work with, after which all this has to be over because the universe can be too cold and because there aren't going to be any neutrons left.
So that's like limiting how many nuclei we can make in the Big Bang.
And also how heavy of nuclei we can make. So if you could keep the universe dense and hot for a long time, you could make things like carbon and iron and whatever. But because it happens so fast and you had such a small amount of time to work with, these things can never be fused in the Big Bang.
So within those rough 15 minutes of Big Bang nucleosynthesis, here's what does happen. Protons and neutrons get bound up into larger and larger nuclei. The first thing to get built are deuterons, which are just bound up pairs of one proton and one neutron. And then you build up into larger nuclei like helium-4, which is a nucleus made up of 2 protons and 2 neutrons.
It turns out that helium-4 is a really stable nucleus. It has a big nuclear binding energy. Once you make a lot of that, it's hard to break it up. And it turns out that about a quarter of all the protons and neutrons get bound up into helium nuclei in this whole few minutes of Big Bang nucleosynthesis. Once enough helium-4 had been built up, it can start to interact with other nuclei to make small abundances of lithium and beryllium. that beryllium, it turns out, doesn't hang around for very long. It decays after about half an hour into lithium. So you wind up with a kind of small abundance of lithium left over. And that actually turns out to be pretty important because we can measure it in things. But it's, in the grand scheme of things, it's not very much lithium that's produced in the Big Bang. By the late 1950s, the main competitor to Big Bang nucleosynthesis, the theory that all the nuclei in our universe were formed in stars, started to show some signs of being problematic. If you look at all the atoms in our universe, it turns out that by mass, about 74% of them are hydrogen, 24% are helium, and 2% are all the other things, from carbon, nitrogen, oxygen, iron, silver, gold, uranium, all that stuff. 24% that's helium turns out to be a really big number. And there's just no way that so much helium could have been formed in stars without producing way too much of the heavier stuff. So what that suggested is that stars haven't been burning for all that long. We now know that they've been burning for, 13.8 or so billion years. And that's a fairly long amount of time. But in the steady state theory, to make 24% of all the atoms take the form of helium, you should have a ton more carbon, nitrogen, oxygen, iron, and all this stuff. So the question became, how could the universe have so much helium? On the other hand, Big Bang nucleosynthesis had a good answer to that. They said a lot of helium would have been formed in the early universe, but its problem was it couldn't make anything much heavier than that. It couldn't explain the carbon, nitrogen, oxygen, iron, all that stuff. So the right answer turned out to be kind of a hybrid of these two theories. The Big Bang created the overwhelming majority of the helium in our universe, and stars made the overwhelming majority of all the heavier stuff. And I would say by the late 50s, that started to look like the most likely answer to these problems.
So with this evidence coming from the content of our universe and where all these atoms had to get made, it seemed like the Big Bang was becoming more and more plausible compared to the steady-state theory. But the evidence didn't stop there.
Around this time, another independent line of evidence also started to favor the Big Bang over the steady state hypothesis. If the steady state theory were true, then the density of galaxies should be the same at all periods of time. So if you take a telescope and look far enough away, which means you're really looking backward in time, you should see the same number of galaxies per volume there as you see in our universe today. But by the mid-1950s, astronomers using radio telescopes were finding that the number density of really bright radio-emitting objects was higher in the past than it was today. In the context of the steady-state theory, this doesn't make sense. But in a universe that's expanding, you could easily understand why there might have been more of these things per volume in the distant past than there are today, favoring the Big Bang theory. So these lines of evidence, both from Big Bang nucleosynthesis and the helium abundance, and the distribution of radio sources in the early universe, while these things did favor the Big Bang hypothesis over the steady state theory, the thing that really put the nail in the coffin of the steady state theory was something called the cosmic microwave background. So if you wanted to make all that helium in the Big Bang, you knew that your early universe during the first few minutes had to be really hot. And that means that there should have been a lot of light in the universe at that stage, enough to be hundreds of billions of degrees. That light should still be in our universe today, just a lot colder and a lot more dilute. And people in the 1950s and 60s tried to estimate the temperature of this radiation that we should all be bathing in right now. And different people made different estimates, ranging from a few degrees all the way up to about 50 degrees above absolute zero. Everyone agreed it would be cold, but they didn't know how cold, and we didn't have measurements that were good enough yet to make a good estimate. But they knew this background should be there. And then in 1964, two radio astronomers, Arno Penzias and Robert Wilson, kind of accidentally detected this faint background for the first time. They didn't know what they were looking at originally, but it turns out that this is the very light that was left behind as a relic from the very first era of our universe's history, when it was very compact, very young, and very hot. We now call this the cosmic microwave background, and it was the observation that really made the Big Bang consensus science and threw out the steady state theory as a interesting but ultimately wrong hypothesis for the nature of our universe. So Fred Hoyle lived until 2001, and he died still rejecting the Big Bang Theory. I was, a grad student in 2001, and I can say it that I don't think I've ever met a scientist, or at least a physicist or cosmologist, who shared Hoyle's view that late in history. By that point, the evidence in favor of the Big Bang was just incredibly overwhelming. To reach the conclusion that the Big Bang didn't happen, by which I mean that the universe some 13.8 billion years ago or so was in a hot, dense state, you have to bury your head in the sand. But he was stubborn. He really thought the Big Bang was pseudoscience. He didn't think it made real predictions, which he's just wrong about. And for whatever reason, he would never change his mind. Apparently, Gould and Bondi, as other, proponents of the steady state theory, were eventually won over by the evidence, rightfully so and very reasonably. But Hoyle just couldn't be swayed. So this is a weird bit of human psychology that I don't claim to understand. And, if it took him until 1975 or even 1985 to reach that conclusion, I guess I could understand it. But 2001 was way too long. And it's really hard to understand that.
So I guess we'll never really know why Hoyle was so stubborn about this. But to be fair, there are lots of reasons to feel uncomfortable about the Big Bang Theory. And probably the biggest one is that not only does it imply a beginning to the universe, but it also kind of implies an end to the universe, or at least the universe as we know it. Maybe the universe will keep expanding until all of the stars and galaxies have burnt out and become so far away from each other that the entire universe becomes too cold for life. Or maybe the universe collapses back down on itself and, reaches another Big Bang kind of situation. But, that idea is heavy to realize that the universe as we know it is not static and it's not going to exist forever. So maybe that's part of why Hoyle never wanted to accept the Big Bang Theory. Why This Universe is brought to you by the University of Chicago Podcast Network. This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.